Welcome everybody to our next chapter. We're going to work on defining integration. We're going to be defining a certain type of integral called the Darboux integral. And in this video, we're going to just lead things off a little bit by talking about what are called partitions. So what is a partition? So first, we're going to be working throughout with a closed interval, AB. And let's say n is going to be some positive integer. So a partition of this interval AB is going to be some finite ordered list that is going to have n plus 1 different numbers in it. So let's get this written down. So a partition of this closed interval AB is a finite ordered list. Now, our sequences were infinite ordered lists. So I want to use some notation which reminds me a little bit of sequences, but has a small change so that we know we're talking about something very finite. So I'm going to say call it x, but instead of using the little bullet, I'm going to use a little square. Okay, a little more rigid, a little more finite. Okay, so it's going to be a list, and it'll be x0, x1, and so forth, only say it's going to have n elements in it. Okay, in fact, I'm going to call this an n partition. Okay, but there's going to be a little bit more to it. Okay, so such that it's not just any list, right? It should have something to do with this interval AB. So such that, well, first, this very first term always should be the left side of the interval. Okay, then the next term should be at least as big as the first term. Okay, we may have some reason that we want to write down a partition where we repeat the same value, so I'll put less than or equal to here. In practice, this is always going to be a less than sign. Okay, so this is going to be an increasing ordered list then. And this keeps going on until we get up to x sub n, and x sub n should be the endpoint, the right endpoint of the interval. Okay, so that is what a partition is going to be. So you could think of this as an increasing function, right? So i.e. x dot is an increasing function from the set 0, 1 through n to r. So it should be increasing, and such that if I take x square of 0, I get a, and if I take x square of n, I get b. Okay. So as an example, right, I might have the interval 1, 6. And I could write down x square, and I could say, how about this could be 1, 2, 4, 6. Okay, and this would be what we're going to call a 3 partition. Okay, and you got to be a little bit careful here with the numbering because it looks like there are 4 numbers, but this first one, right, gets an index of 0. So we only count, really you should think of this 3 as counting how many intervals we get, right? 1, 2, 3 different intervals, or if you like, you could count the commas. 1, 2, 3 different commas. Okay, so this would be a 3 partition. Notation-wise, I'm going to use the following. So I'm going to use kind of a cursive P. This will denote, especially if I put AB after it, okay, equals, and very often when the notation or the context is clear, I won't write the AB. This is going to equal the set of all partitions of the interval AB. Okay, that way I can write things like, say x dash or x box is an element of P. Okay. If I want to tell you what type of partition it is, like a 3 partition or a 5 partition, then I'll use a little subscript n. So this would be the set of all n partitions of AB. Okay, so up above, this x was a 3 partition, so I'd say this x square is an element of the 3 partitions of 1, 6. Okay, so there we go. There's some other notation I'm going to introduce here. This is not at all common notation, but it'll be helpful for us to have it at least for a little bit. So first, the terminology, and this is fairly standard, is if, say I have a partition W such that each term of this partition, say that we had up above X, is a term of W. So, for example, when I'm looking at 1, 2, 4, 6, and then maybe I have a W, it's got to have the 1, and, well, let's see, what if it just had 2, 3, 4, 5, and 6? So now every term in X, 1, 2, 4, 6, is a term in W. So that's the situation I'm looking at. So if that's the case, then we call W a refinement of X. So you start maybe with some X and you add more terms to it. And when you do, you get a refinement. Okay? Not too bad there. Now here's the interesting bit. Okay? So now we have another partition, Z. So Z is some partition. Then the ordered list obtained by combining. So let's take this original one, X, and this new one, Z, into one partition. Okay, so into one partition. And how am I going to do that? Well, I do it by just taking all of the terms in X and Z and putting them together and possibly having to sort out the order, right? Because this has to be an increasing function. Okay, but that's a pretty easy thing to do. Everything is finite, so there's no question of whether this is a terminating process. So I combine them all into one partition, right, of AB. And so because I'm combining these, I'm going to get more stuff, and each of these original partitions is going to have this more stuff partition, the one that combines them, as a refinement. So we're actually going to be called, so we're going to call this called the common refinement of X and Z, and denoted by, and I'm just going to take the X and put a little wedge, okay? This little wedge symbol. Looks kind of like a V, but it's a little higher. You might think of it as an OR, all right, from logic, but this is the notation we'll use for a common refinement. So as an example of this, let's say I still have this, we'll do this in green. If I still have the same X from up above, so I'm still working in 1, 6, I still have that X is 1, 2, 4, 6, And let's say that my z is going to be 1, 2, hey, 3.5. That's right, I didn't say it had to be integers. Okay, that's important. 4.5 and 6. So then, if I want to build the common refinement, then I'm just going to put all of these together into one. And I could put duplicates in, but that's another thing I'm going to just say. I'm not going to include duplicates because there's no real need to. So I'll do 1. Okay, that handles these. 2, that's the next one in both, so I can just put 1, 2 down. Let's see, 4, 3.5. Okay, let's do 3.5 because we got to make it increasing. We got that. Next is 4.5 or 4. Let's do 4. Then 4.5. Okay, and then 6 or 6. Okay, they're both 6. So there we go. So I now have a refinement of both x and z. And pictorially, I might diagram it like this. I have my x, I have my z, and now I have this x join z. Okay, up above. Okay, so if I need to diagram things, you might see me do stuff like this. Okay, so there we go. Now we are going to be using these partitions and these refinements as building blocks for our integrals. So in the next video, we're going to define what are called the lower and upper sums of a function with respect to a partition. So you got to understand this partition first, and then we can do lower and upper sums, and that will be one more stepping stone to integration. All right, we'll see you next time.